a little bit, just a little bit. Yeah.
Just one.
All right. So Angeli just presented one of the work in the problem of the image synthesis from text, right? So given text, so we try to generate some images according to the text. So this one is a paper that I consider baseline. Actually, this one is not directly compared inside Angeli's paper, but it's one of the related work. And in the paper, they mentioned this one as a contemporary work, which is okay, but this one appeared a bit earlier. So this paper named Generating Images from Captions with Attention. So the problem is the same. You are given a piece of text and you are asked to generate an image. So this example summarize the goal of the paper. So basically you are given this text, and then this one is a generation process of the images. So this text is this digit 7 is at the bottom left of the images. So they try to generate over time, and then this one is the final result. And similarly with this one, like the digit 3 is at the top of the digit 1, which is we have this at the final result of this paper. So before going directly to the this paper, because this one is built on top of this paper. So this one is another paper appeared a bit earlier, previous year. The paper that I'm presenting now. This paper, they only focus on the problem of the image generation. So there's no text here. So image generation is similar to GAN. This one is an alternative to GAN, another solution to generate images from noise. So let's say we start from an autoencoder, which is there's images. We encode to the latent space and we decode it to get the image. So for example, here we have Preferred.AI image. We compress and then we decode. We might lose a dot here because of compression effect, for example. Then this one is the autoencoder kind of model. But then we want to learn a generative model, which is without the encoder, without images. We random some noise here, and then we sample some noise here, and then we can generate image. And this one, they proposed a framework to use INN to generate image. So basically, the architecture, there are two parts, the encoding part and the decoding part. And each one is constructed by an INN. So this part, the encoding part, they read from images. And then the other part, they into a latent space, and then over time, they try to decode it, and then they write. So the write operator here is they just output to the canvas of images, and then it's overwrite over time, and then in the end you're gonna have the images. So basically there are two things, because there's two things to optimize here, because in the end you want to cross this one, because we don't have, in the inference we don't have images anymore, so we want to sample some noise to generate image from here to here. So there are two things to optimize. The first one is the log likelihood, which is we want the image to be real, right? So we optimize it. This one is the reconstruction loss. And another thing is that they try to minimize the KL divergence between the real image here and then with some noise. So they try to force the latent space to form to be similar to some distribution that we can sample from. So most of the time they use the Gaussian here. So there are two things optimized for this paper. So this one is equivalent to GAN, another solution to generate image from noise. And the generation process is something like that. So as I described, right? So this one is an INN process. So as every time step, they're gonna write to a canvas, and then over time they're gonna have the sharper images. And then let's say you set the time step to 20, so you write 20 times, and then you're gonna have the final result here, for example. So yes, so this one is a paper that I'm trying to present today, which is the generating images from captions, pay attention. And this one based closely to the one that I presented. And this is the whole architecture. What they are trying to put in is the text encoder. And they, so the text comes from it's modeled using a bidirectional INN. And then at each time step, each word is gonna output hidden state of the forward INN and the backward INN. So they concatenate it. So each word we're gonna have the representation of the word. So they try to input the text information inside the image generator. So here we have RNN as image generator. So at each time step, they're gonna they're gonna look back to the text. So which word inside the text we're gonna focus to generate the canvas to write to the images, which is they use the attention mechanism here. So well, it's nothing but like the difference from this one to the previous one is that at every time step they don't sample the noise independently for each time step, but here they condition on the previous time step, which is the z. The time t is conditioned on the previous z, and this one is formed as a normal distribution, which is parameterized by the hidden state of the encoder here. So there's another thing is that at each time step the hidden state of the RNN here to generate to write to the images is constructed by the LSTM, which is come from the input of the noise and the text, and the ST here is from the attention mechanism. So every time to write something, they look back to the word, they look back to the whole text, all the words, and then they try to compute the weight, attention weight. So which word you're gonna focus on, and then you're gonna generate the you're gonna input it to the generative RNN here, and then write to the image. And so the objective here is similar to the previous one, but there's they also condition on the text. So the Y is the text, and so that's it. Here is some qualitative examples of the paper that they show. So they show that actually the image generator can actually condition on the text when they actually change some part of the text. For example, here they change the color in the caption, yellow, red, green, blue, and they're gonna generate kind of similar. The image is not sharp because of the limitation of the generator, the image generator. But the idea is that the generator actually can condition on the text. And here's another set of examples when they change some object. And in this paper, they compare with a few of the baselines, which is this one is the proposed one, and the other one is some of the kind of autoencoder kind of model. So you input text and then you generate the images. And they show that this one is more likely to generate some images, some shapes that look more similar to the real ones. So that's the idea of this paper, and this one is comparable to the one that Angelis just presented. So now I want to come to some review questions to the paper that's just presented by Angelis. So everyone, just refresh your memory a little bit about the paper. We already observed few of the images. It's very nice, right, from Angelis paper, right? So my first question is, does the noise, the Z, play any role in the generation process, the image generation process? So this is my first question. So basically, as you remember, right? So the image generator gonna take the noise and the text embedding to generate images. So does the noise here, the Z here, play any role? Because basically they can generate directly from text. And the reason why I ask this question, because there's another follow-up questions, which is, I think not the GAN is the main factor to generate that nice images, but the joint-embedding learning is the most important factor, which is Angelis didn't present it at the beginning. So actually, the model, they learn the text encoder separately, and the idea is that so before they train the model, they have the text encoder, which is they learn it separately at the beginning. So the idea is that they try to align the embeddings of the text and the images first before they come to the image generator. So they take the image embeddings from let's say some pre-trained CNN, and then they input the text to the text encoder. They get the same embeddings. And the idea is that they try to align the embeddings in the latent space, which is, this technique is applied to most of the multimodal retrieval problem when they try to align the latent space of the different type data. So in this case, image and text. And there's one limitation here for this particular approach, is that they require another source of labels, which is in the dataset that they use for in the English paper is they use the kind of image captioning dataset, but there are auxiliary information where the image belong to some classes. For example, like which type of flowers or which type of bird is it. So then, based on this source of information, they try to align the embedding first. So then come to the phrase that when they learn the image generator, they fix the embedding of the text encoder. So they just input the embedding that they already learned before to the model, and then they learn to generate image. So which I argue that the text embedding there is already capture most of the important information about the images at the beginning. So that's why we have that nice images. Where they come to another data set, which is the Microsoft Core called image captioning, which doesn't contain any other label information. So they cannot learn the alignment at the beginning. So they learn end to end, which is the output of images doesn't look that nice compared to the previous ones. So that's why I think that the joint-embedding learning at the beginning is the most important thing to the image quality. And this one is not generalized to all the data set. So another question is that, like, should they compare with some existing baselines, in the sense that from text to image, right? We can simply apply the autoencoder kind of family. So you input text, you can generate image. So you can learn that from the data, and then you, in the future, you can input some text and you generate image. Because the problem is that you only have text, so you try to generate image. And you can also have some simple baselines, like you can put the text conditional kind of image generator, which is the one that is introduced in the paper that I presented, which is you just input for example, the draw paper, you just input the text embedding at the input of the INN, then you generate the image. So you can learn the model that can generate image from text. So yeah, that is my 3 patterns. So yes, Angelis, can you give some thought about this?
Okay. So about the first one. Okay, does the noise plays any role? Yes, so according to what they show, it seems like it captures some other factor of variation, like style or background information. So it plays the role of some kind of uncertainty. You know that you would generate some kind of images, but you don't know what would be the pose or the background of the images, because there may be many possibilities, even for a single description. So that's the whole idea behind this, and they kind of show in the experiment that indeed it captures some useful information. Yeah. So the text here is really about the content of the image, the main content, whereas this noise is more about some factor of variation that doesn't affect the content, but can still affect things like the background or whatever.
Is it very important because the text most of the time is contained all? I mean, it can also contain background, right? Because like some walk on the white snows or whatever.
Yeah.
So it contains colors on this background.
Yeah, but not always, and you don't know the pose. Also, if you consider, for example, the tiger is hungry, we can see many different poses of this corresponding to this description. So it's more to inject some uncertainty and to learn more robust generator.
If you say that it's inject uncertainty, which is I argue that it's going to be ignored when they train the embedding at the beginning. They try to align embedding at the beginning, and they don't. What I mean is that they don't retrain the text encoder. So they use the text encoder and they train with the the label information at the beginning, and they directly input the embeddings they already learned. The text embedding here is not learned anymore. So when they learn the generator, this one is fixed. The embedding is fixed, and this one is already well aligned with the image feature at the beginning.
Yeah, but the noise is about the generator. So when you input the text to the generator, there may be many possibilities.
So what I mean is that even from this one only, the generator can already fool the discriminator because all the important information already captured inside this one.
Yeah.
To fool the discriminator.
But the generator tries only to fool the discriminator in terms of generating something that looks real, not something that looks exactly as the corresponding real example.
No, which is they can ignore the noise because this one is kind of already used to fool the discriminator.
Yeah, whether it can ignore the noise, yeah, it can ignore it. Now, the purpose of this noise is to introduce this uncertainty that I mentioned. Whether the generator can ignore it, of course it can ignore it. But based on what they saw in the experiment, it seems that it doesn't always ignore it. Yeah, but of course, the generator is free to ignore it.
Yeah. Okay, so because the second question is about they learn the joint embeddings, right? So the point that they learn the joint embedding at the beginning. So what I mean is that if you learn at the beginning, so it might the noise might contribute more in the sense that it might provide the generator more information about this. But because the text embedding here is already compressed. It's already compressed to align with the image feature. Mm-hmm. So what I mean is that all the important information here, all the important information here is already have the generator to generate the image here. So what I mean is that this play like smaller role and maybe ignore. I mean it's more likely to ignore when you already train everything from beginning. And another thing is that this part, right, contribute to the image quality. As I told you, like the example that you all show is from the data set that they already have the label information they learn from. But if, for example, this one is from the Microsoft Coco data set, which is doesn't contain the class information, which they cannot learn the embedding at the beginning. So the image quality is well, it's okay. I agree that this one is sharper than the previous one because the previous paper is this one they use the default to generate image. The other one they use the binary, which is less sharp than this one. But the image quality is I mean the information here, the image doesn't look that real anymore.
Okay, well, I think there are two things in terms of image quality. So what I mean by image quality here is about the sharpness of the image. Now there are two things. One in terms of the sharpness, then definitely GAN is the one who will generate the sharp images. Like the VAE objectives, they will always lead to blurry image, and we can prove it theoretically why. Now, the second factor of quality is whether the content of the image itself is faithful to the caption. Here I agree with you that what they did in the beginning does matter actually.
It's better a lot.
Yeah, it does matter actually, and it helps a lot to generate something that is faithful. Now, the paper that you presented, they would probably learn to generate something more faithful but blurry. So here they will learn to generate something less faithful but sharper. So that's the difference between the two approaches. Now, the ideal thing to do is to try to reap the benefit of both approaches, both to learn to generate sharper images and who are faithful to the description. Because the problem of the blurriness in the VAE framework is due to the objective they use. Like the KL divergence they use there tries to map your distribution to something that is broader, like to the whole Gaussian space. Yeah. So sometimes it will pick up something that doesn't look real.
I think that is I think it's another one which is There's some basic baseline that they can compare with, I think.
Yeah.
I think.
Yeah.
Like
Yeah.
from text to image.
Definitely, yeah.
Which in this paper they only give some variants of their model and then we just show.
Definitely. I think the point is just maybe they almost all appeared at the same period.
Oh no, this one is appear earlier, right? This one is all compared inside this paper because the
they
autoencoder,
cite them, right?
The autoencoder.
Yeah.
That's not. I mean the autoencoder is appear much earlier, right?
Yeah.
Like you can put the text and then you output the image.
Yeah.
It doesn't need to have some new technique. And even the VAE or draw images which appear like 1 year, 2 year earlier, which is can generate images.
Yeah.
Which they can just put the text and input and then you can generate image.
Alright.
So this one, some of the baseline that I think that the paper can compare with.
Yeah, definitely.
Okay, we should end here.
I think we have some issue.
What's the number of the rider?
Oh, I need to get it. Number of
I think this is the one.
Oh, they didn't leave it in the basement, right? In the office. Security.
Basement?
No, level 1.
No.
You didn't ask them.
They left it there?
Maybe, I don't know.